Hey everyone, in this video we're going to be learning about the strategy for testing series, or also section 11.7 in the textbook, which is in the description. So in this video we're not going to be learning any new series, but we're going to learn about how to choose the right test. So the goal of this video is that whenever you see a series, you want to be able to identify it, and for that we're going to go through how we identify series and a lot of examples explaining how we know that what test we use for what series. So before we start, I'm going to go over a quick recap on all the series we learned. So the first one, we have the divergence test. So for a series a sub n, if the limit as n approaches infinity does not equal 0, we say the series diverges. So remember that if the limit does equal 0 for this test, it doesn't prove convergence, but it just shows that we need to use another test. And then the next one, we have geometric series. And then a geometric series has a form a plus ar plus ar squared plus ar cubed all the way, or in the summation notation of ar to the n minus 1. And a is the first term and r is the common ratio. And this series converges if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than 1. Next up we have p series, and p series has the form 1 over n to the p, and this one converges if p is greater than 1, and it diverges if p is less than or equal to 1. Then we have the integral test, which is saying that if your term is equal to a function and that function is positive, continuous, and decreasing, then the series and the improper integral either both converge or diverge. Then we have the direct comparison test, which for positive term series, if 0 is less than a sub n less than b sub n, and b sub n converges, then a sub n converges. So if the bigger series converges, the smaller series will also converge. Then if 0 is less than b sub n, which is less than or equal to b sub n, less than or equal to a sub n, and your smaller series diverges, then the bigger series will also diverge. Then we have the limit comparison test, which if the limit as n approaches infinity of the ratio of the two terms of a sub n over b sub n is equal to c, where c is a number between 0 and infinity, then both series have the same end behavior. Next we have alternating series test, which if the series has the form negative 1 to the n times the term, or negative 1 to the n minus 1 times the term, then with the term being positive or greater than 0, then this converges if the next value in the term is less than or equal to the current term, or b sub n plus 1 is less than or equal to b sub n, and the limit as n approaches infinity of that term equals 0. So you'll automatically think of alternating series tests when you see this right here, this negative 1, the alternator. Whenever you see that, the first thing you should think about is alternating series. Then we have the ratio test, which is just the limit as n approaches infinity of the next term over current term, or a sub n plus 1 over a sub n. Then if L is less than 1, we say the series is absolutely convergent. If it's greater than 1 or it equals infinity, we say the series is divergent. And if it's equal to 1, then the test is inconclusive. Same thing for the root test, just a different formula. You just take the nth root of the absolute value of the term, and if your L value is less than 1, the series is absolutely convergent. If it's greater than 1 or equal to infinity, it's divergent. And if it's equal to 1, then the test is inconclusive. Now we'll be thinking about, this is like a thought process, I guess, to see if you're confused on how to approach a series. So this is how I would like to think about it. First of all, let's see. You would think about if the terms go to 0 in the long term, like if you can I guess know that when you take the limit in your head, do they approach 0? Is it geometric? Is it a p series? Is it positive and similar to a known one? Remember, that's direct comparison. Is it alternating? Does it have factorials or exponentials? That should scream root test. Is the whole term, ratio test. is the whole term to the nth power, then that screams the root test. Remember, power, to undo power, you take the root of it. I guess that's a way to think about it. And then lastly, does it come with an easy improper integral? I'll be honest with you, improper integrals are really like uncommon, but they're like, I guess it's normally going to be like 1 over a function. Whenever there's an improper integral series problem, like it'll normally be like you'll like be able to identify it really quickly. It'll be like, I don't know, like let's say it's like 1 over, I don't know, let's say just sine of like x or something like that. Like the function will look something, it'll have like something to over 1 over, it'll be a fraction. And normally, think of the improper integral as the last one. The only reason I put this one last to think about is because sometimes you may think that, oh, like you might see 1 over n squared and be like, oh, well, this is positive, continuous, and decreasing, but you should also notice a p-series. So first, go through every single other test first and identify. If it's not, then it's probably an improper integral. That's why I put it last. So now, let's start with the examples. So, our first example, determine whether 3n plus 1 over 2n minus 5 converges or diverges. So, we know that this is not a geometric series because there's no like common term or common ratio. We know this is not a p-series, and we know there's no alternator, there's no factorials, there's no root. So the first thing we should do is we should test the divergence test, because the term looks really easy to take the limit of. So we know a term, so our a sub n is going to be equal to 3n plus 1 over 2n minus 5. Right? Now we need to take the limit of this. So let's take the limit as n approaches infinity of the term. So to find the limit of this, we're gonna divide the top and bottom by the highest power of n. So here, the highest power, both of them are, they're just n's, right? So we can divide every single term by n, since that's the highest power. So it's gonna be equal to limit as n approaches infinity. Remember, 3n divided by n is just 3. 1 divided by n is just 1 over n. Now we do the same thing for the bottom. 2n divided by n is just 2. And, whoops, that's a minus, sorry. 5 divided by n is just a 5 over n. So this is what you should get. So now we can evaluate the limits. So we're gonna, the top is gonna stay the same, the 3 is gonna stay the same, so 3 plus, remember 1 over infinity is just 0 over 2 minus, remember 5 over infinity is 0. So this is just equal to 3 halves. And if you're, and you know, so since the limit as n approaches infinity of a sub n of the term is equal to 3 halves, and you know 3 halves is not 0, so we can say the series diverges by the divergence test. That's your answer. Sorry, I spelled test, or test does not look like it's spelled test. So we know this diverges because, remember, the divergence test says that if the limit as you take approach it does not equal to 0, then the series diverges. So, you know, this one was equal to 3 halves, so we can show by the divergence test that this one will diverge. Hopefully that was a pretty easy problem. Now let's move on to our next example. So example number 2. Determine whether 4 over 5 to the n power 5 to the n, sorry I can't talk, converges or diverges. So if you know, you can take, so like for every single thing you learn in calculus, like let's say integrals, right? Like let's say you had the integral of 3x squared, right? You can always just take out a 3, right? Because it's a constant, so you could just leave it as 3 times the integral to the x squared. So you should know that you can also do the same thing with series, right? So we know that we can rewrite this term as we'll just factor out the 4 times 1 to the 5th, and we raise that to the nth power. Now you might ask that, hey, only the nth power is only on the 5. Yes, but whenever you factor out the 4, right? What is 1 to the n? So whatever number you plug in for n is always going to equal 1. So like let's say n equals 20, 1 to the 20th power is just 1, right? So the 1 is not changing, so we can rewrite this whole entire term to the power of n since we factor out the 4. So this means that every term is made by multiplying by the same factor of 1/5. Therefore, if you remember, this has a common ratio. And whenever you see something like this should scream. I know there's a little pause because I want you to think about it, but common ratio should scream you geometric series. So hopefully that's the first thing you thought of. So we already rewrote the series. Now we know our first term, which is our a value, is just 4. So a is equal to 4. And then we know our common ratio is just 1/5. So now we apply the geometric series rule, and we know that a geometric series converges if your r value, the absolute value of the r value, is less than 1. So we know that the absolute value of 1/5 is just equal to 1/5. And I hope you guys know that 1/5 is less than 1. So this converges. So, well, the series converges by the geometric series test. And I know this is not in the question, but just really quick, you know that whenever a geometric series converges, your sum is equal to a over 1 minus r. So sometimes a question, well, geometric series is really easy to find, right? But sometimes you have to like understand, like it'll be tricky. So whenever if you see like a problem like this, remember you can always factor out constants. So maybe try factoring out constant and see that. In this case, I saw that it's 4 over 5, and I saw if I factor out the 4, I could raise the whole entire thing to 1/5 to the n, which screams geometric because it's easier to see that way, right? So whenever you have a geometric series, maybe not most of the time, but a lot of times they'll ask you for the sum, and you remember the sum is always equal to a over 1 minus r. So in this case, it's just 4 over 1 minus 1/5, and this is just equal to 5. 1 minus 1/5 is 4/5. Then you multiply reciprocal. So 4 times 5/4. So that's just 20 over 4, which is 5. That's how I got 5. But just in case that, remember that if it converges, also memorize the sum formula, the a over 1 minus r, because a lot of times they do ask for that. So I know it's not part of the question, but I just wanted to bring it up. But the series does converge by geometric series test. Alright. For our next example, we have determine whether 1 to the n to the power of 3/2 converges or diverges. So, if you see that this looks way too similar to this, 1 over n to the p. So, we know that this is a p series problem, right? In this case, our p value, in this case is 3/2. And we know that a p series converges if, we know a p series converges if p is greater than 1. So now we know that, if you don't know, 3/2 is also equal to 1.5, and 1.5 is greater than 1. Therefore, this series, or if you don't want to write this series, you can just write the original formula, converges. You can just leave it as that, or you can just write converges by the test you use. So by the p-series test. I like writing this because just sometimes, like, even though teachers know what you used, they want you to state like this converges by the alternating series test, this converges by the integral test. They always want you to write the test down sometimes, but if they don't care, I'll just write that the series converges. Now we move on to our next example. Determine whether 1 over n squared plus 7 converges or diverges. So we know that this is not a p-series, right? This is not geometric. There's no common ratio. There's no alternator. There's no factorials. There's no exponents or exponentials. There's no roots. However, when you look at this example, you should see that this looks really similar to a p-series, which is just 1 over n squared. Sorry, the p-series 1 over n squared. It looks really similar to 1 over n squared, right? The only thing that's different is it has a plus 7. So we know that this is the comparison. If you take the inequality for this, that comparing these two inequalities is really simple. So for this, we will be using the direct comparison test, because you know that none of the other tests make sense, and you know that 1 over n squared plus 7 looks really similar to 1 over n squared, right? So for direct comparison test, we need our two terms. So our first term is just 1 over n squared plus 7. Our second term is just going to be 1 over n squared. So we know that n squared plus 7 is greater than n squared. So if you take the reciprocal, we get 1 over n squared plus 7 is less than 1 over n squared. And you can always plug in numbers to prove it's true, but we know that this is true. So we know that for the first thing, we know that the term is decreasing. So where we get something like this, right? This is a theorem. So we know that in this theorem, right, if the bigger series converges, then the smaller series will also converge. And we know that the bigger series, in this case, is 1 over n squared. So we need to check if this one converges, so which is equal to. And we know that this series converges by the p-test, or sorry, not the p-test. The p-series, this is a p-series with p equals 2. And since 2 is greater than 1, this series converges. So I'll just write converges by p-series. So we know the bigger series converges, therefore the small series also converges by direct comparison. So as your final answer, you can write 1 over n squared plus 7 converges by the direct comparison test. I'm sorry for if I was kind of like a little confusing, but you always want to think, right, whenever you, like, an easy way to identify something direct comparison is going to be like something like this, right? It'll be like 1 over maybe n cubed plus 69. So like they'll try tricking you, right? Like just think about it, right? The constants, like the plus 7, whatever they throw you, plus 6, 7, plus a million, all that stuff doesn't matter, right? Because as you approach infinity, whenever you have infinity squared, you think the plus 7 is going to matter. The plus 7 is not going to make a difference. So you should always think of, you're going to compare it something to something similar, right? Without the constants. So just look at similar series, you know, or Matter of fact, just use the same power as to compare the series to. Like let's say I gave you a problem where it was 1 over n cubed plus 40. You just want to compare that to 1 over n cubed, right? Just pretend that plus 40 doesn't exist. So I guess that's an easy way to know a direct comparison. But for this example, this one converged by direct comparison test. So next one, example 5. Determine whether n squared plus 1 over n to the 4th plus 3 converges or diverges. So whenever you see like these type of problems where there's like 2 powers of n, so you want to like subtract the 2 powers, right? As we explained in the last example, the plus 1, the plus 3, the constants we don't care about those, okay? Those don't matter. So we want to see that. So this is also a comparison test, but this is the limit comparison test. Why? Because remember, we use a limit comparison test when inequalities are messy. We don't want to compare like n squared plus 1 over n to the 4th to like some random inequality, right? We can just take the limit as this and see what it behaves like. So whenever we see like 2 powers of n, you always want to like simplify this, right? So let me rewrite this and show you what I mean. So we have n equals 1 to infinity of n squared plus 1 over n to the 4th plus 3. So as we approach infinity, these plus 1s and plus 3 don't matter, right? So it's going to behave something like this. So only these terms matter. And if you know, when you divide exponents, you subtract them. So this is 2 minus 4, so this is also equal to n to negative 2, or 1 over n squared. So we're going to be comparing this to 1 over n squared, because that's what this whole entire thing behaves like, right? So we're going to let our first term, it's always going to be the term that's given. So n squared plus 1 over n to the 4th plus 3. Our second term we're going to be comparing this to is just 1 over n squared. Because why? Because in the long run, this series behaves like 1 over n squared. Now, you know we need the ratio a sub n over b sub n, so we're going to form the ratio. So a sub n, or your first term or second term, so it's going to be n squared plus 1 over n to the 4th plus 3 over 1 over n squared. Now this does look messy, but remember when you divide a fraction, that means you multiply by the reciprocal. So we're going to multiply all of this by n squared. So this is going to be equal to, we're multiplying by n squared, so n squared times n squared. Remember, when you multiply exponents, you add them, so 2 plus 2 is 4, n to the 4th plus 1 times n squared is just n squared. The bottom stays the same. So you have n to the 4th plus n squared divided by n to the 4th plus 3. Now we want to take the limit, right? So, I have space here. So we're going to say the limit as n approaches infinity of n to the 4th plus n squared over n to the 4th plus 3. Now, whenever you see this, you always want to divide by the highest power. In this case, the highest power is to the 4th power, right? N to the 4th. So we're going to divide every single term by n to the 4th. So it's going to be equal to the limit n approaching infinity. N to the 4th divided by n to the 4th is just 1. N squared divided by n to the 4th is just 1 over n squared. Why? I'll show you really quick. So n to the squared over n to the 4th. Remember, when you divide exponents or powers by a fraction, it's used to subtract them. Oh, sorry, that looks like a 3, not a 2. You just subtract them, so 2 minus 4 is negative 2, and to make this positive, you just write it as 1 over n squared. So that's where you got the plus 1 over n squared from. Then on the bottom, n to the 4th power divided by n to the 4th power is just 1. And then 3 divided by n to the 4th is just 3 over n to the 4th. Right? So now we can finally take the limit. So the limit is n approaching infinity of 1 plus 1 over n squared over 1 plus 3 over n to the fourth is equal to, it's going to be 1 plus 1 over infinity squared is just 0. We've done this a million times. A small number divided by a huge number is just 0. Bottom's also going to be 1. 3 divided by infinity to the fourth is also 0. So 1 over 1 is just 1. Before we got the limit to equal 1. So we know that since the limit is a positive finite number, and in this case our c value was between 0 and infinity, that's the conditions for the limit comparison test. So our final answer is going to be, because 1 over n squared converges, the original series converges. So if you see if you see two powers of n or on a fraction, you should always think of limit comparison test. And to know what to compare to, normally just take the two highest powers. So in this case it was n squared and n to the fourth, and just divide them and see what you get. So in this case it was just 1 over n squared, and just compare to that. And that's basically all the limit comparison test is. And you just take the ratio and you take the limit. Now, time to move on to our next example. This is a really classic example, or a really common example that I see, and this one gets a lot of people, so we'll explain. So determine whether 1 over n times the natural log of n converges or diverges. I like to write my natural log with I don't know what it's called, a cursive n, or a loop-de-loop thingy. I don't know, because it looks cooler, but it's a natural log. So let's think about this. So we know a natural log is positive. We know there's no common ratio. We know this is not geometric. We know this is not p-series. We know this is not alternating. So remember, this is something that, remember what the last thing I told you, that whenever you think whenever you run through all the tests and you see that this is not any of these, this is probably an improper integral. So the integral test is probably the most natural choice for this. So when you find our function, well, whoops, why am I writing in blue? So we'll say f of x is just equal to, remember, just replace the n's with the x's. So 1 over x times the natural log of x. And in this term, the bounds are 2, right? And this, you see, it has n equals 2. So we know for x is greater than 2, this function is positive. Natural log is positive all the way. For x is greater than 2, sorry. We know it's continuous, and we know that this is decreasing because it's 1 over a function. So we can apply the integral test. And if you can't see it's decreasing or whatever positive is, just plug in a lot of numbers. Obviously, I don't know what the natural log of 3 is, but I know that 1 over 3 times, or 1 over anything is, and as it gets bigger and bigger, it's going to go smaller and smaller, right? Kind of like why 1 over infinity is 0. So now we've got to set up the integral. So it's going to be from 2 to infinity of 1 over x, natural log of x. Now you can't tell me this is not the best integral, this is not the cleanest integral sign you've ever seen. That was a masterpiece. I have to glaze myself there, my bad. So this is kind of a confusing integral because how would you start? Well, for this, you kind of have to see, right? This is a u substitution, right? Why? Because you see there's two x's, right? We have a natural log of x and an x. So if you know the derivative of natural log of x is 1 over x, so we can cancel out this x right here, if that makes sense. So I'll show you by when we do it. So we're going to use a u substitution. So u is equal to the natural log of x, and du is equal to 1 over x. I forgot to write the dx on the end of the integral, I'm sorry. 1 over x dx, and then dx is just equal to x times du. Remember, we just multiply reciprocal. Now we can rewrite our integral, right? So it's equal to one over x times u times x, because the dx, right, we're just replacing the dx with x du, and then the natural log of x is just replaced with u, so you see the x's cancel. Therefore, you get the integral to be 1 over u du. Now, all you gotta do is plug in the bounds. Oh wait, I'm sorry. We did not take the integral of 1 over u du. So if you know the antiderivative of that, the integral of, I'm getting ahead of myself, of 1 over u du is just the natural log of the absolute value of u plus c. Now we can plug it in from infinity to 2. So we're going to have in parentheses, oh yeah, I'm sorry, I'm getting ahead of myself again. We also need to replace this, the infinity with a limit, so this is also the limit as b approaches infinity of natural log of u plus c. So this is from b to 2. Remember, when you have an improper integral, you replace the infinity with a b, and then you just write the limit. So now we can finally plug it in, since I'm not ahead of myself this time. So it's going to be the limit as b approaches infinity of the natural log of, well, u was equal to natural log, so this is going to be the natural log of the natural log of b minus the natural log of the natural log of 2. So now we have to plug this in. So the natural log of the natural log infinity, so the natural log infinity is infinity, and then you have to take the natural log again. Actually, this is super confusing. Let me just write it like this. So natural log of b approaching infinity is just, so we know this part right here, the b value, this is just equal to infinity. So this is just going to become the natural log of infinity minus the natural log, I do not know what the natural log of 2 is, so we're going to leave this the same, minus the natural log of the natural log of 2. So we know natural log of infinity, this is just equal to infinity, right? And we know that natural log of 2 is some number, and then that's going to be the natural log of like some random number, right? So this is going to be like infinity minus a small number, right? So we can write infinity minus hashtag for number. And infinity minus a number is just equal to infinity. So we don't need to know what the natural log of 2 is, because we know the first term is infinity. Therefore, we know that this integral diverges. So we can say, since I don't like writing out all the text, so I'll just write in the math notation. So since of, hold up, what was it again? 1 over n times the natural log of n diverges also diverges by the integral test. So there's our answer. This one's a little bit hard, but we couldn't like really like take any like tests for this. And I guess if you could say that, what about the divergence test, right? Well, if you take the limit, right, 1 over 0 times the natural log is 0. What's 0 times anything? 0. And 1 divided by 0 is undefined. So that test doesn't work. And we know that this was not a p-series geometric. And all the other tests didn't work, so we have to take the integral test. So for this one, I guess you kind of have to be good at integrals, but you've been practicing integrals hopefully a lot, so you should be familiar with integrals. So this was just a use of problem, but yeah, that's basically it. Just check the conditions if they work, take the integral, and if it diverges, then the series also diverges. Diverges. I don't know why I said diverges is. Now let's move on to our next example. Determine whether -1 to n minus 1 over n to the 1/3 converges, diverges. So what do you see in this problem? Boom, it's the world's famous alternator. So this should be screaming one test in your head. And the only test that should be screaming in your head is the alternating series test. So our natural choice will be the alternating series test. So our first thing, we're going to identify the term. So I'm going to rewrite the series, by the way, like I always do. So n equals 1 to infinity of -1 to the n minus 1 multiplied by 1 over n to the 1/3. Sorry, it does not look like a third, 1/3. So first thing we need to do is to check if this term, the b sub n, is your term decreasing and as the limit approaches 0. Well, we know as this bottom, as the n gets bigger, we know as we plug in more and more numbers, n gets bigger, n to the 1/3 gets bigger. And 1 divided by a bigger number means it's getting smaller and smaller and smaller. So if you plug in numbers, I don't want to plug in numbers because this is a messy thing, but you can test it yourself. So if you plug in numbers, that this term will eventually get smaller and smaller. So we know that this is decreasing. So now let's check the limit. So the limit is n approaching infinity of 1 over n to the 1/3 is equal to 0. Remember, 1 over infinity to anything is just 0. And we know that the infinity to the 1/3 power is just infinity. So both of these conditions are true, so let's say the series diverges. By the alternating series test. Now we're going to our next example. Determine whether n factorial over 5 to the n converges, diverges. If you remember last video, I told you whenever you see a factorial, that should scream ratio test. Period. Factorial, first thing you want to do is ratio test. That's all you got to do. Now these are the most complicated ones in terms of simplifying, and because of the factorial, but we'll knock this down together. So first thing we want to do is write out our term. You know our term is just n factorial over 5 to the power of n. Then you know we need our a sub n plus 1. So just add n plus 1 to everything. So this is equal to n plus 1 to the factorial over 5n plus 1. Now let's form the ratio. We need a to the n plus 1 over a to the n. So to form the ratio, looks like that. Well, you take the absolute value of this, but we know that every single term here is positive, so I just skipped the sign. So our ratio is going to be Sorry, I couldn't see the first term. So when you multiply this by the reciprocal, so we're going to multiply this by 5n over n factorial. We're going to get n plus 1 factorial over 5n plus 1. Multiply this by 5n over n factorial. Now, let's simplify. So before we start, I don't know if you remember last example, but n plus 1 factorial is equal to n plus 1 times n factorial. I explained it last video why this was true. You can memorize this if you want to, but you should always if you want to quick visualize, I'll explain again. So let's plug in a number, right? So let's say we plug in 3, right? So this is, if you plug in a 3 to n plus 1 factorial, that's going to be 3 plus 1 factorial, which is equal to 4 factorial. And we know 4 factorial is just 4 times 3 times 2 times 1. However, when we simplify this to n plus 1 times n factorial, you're going to be like, what if that changes? So let's plug in a 3 again, right? So when you plug in a 3, that is just 3 plus 1 is 4. So 4, this is just 4 times 3 factorial. And if you see in the first example, this is 4 times 3 times 2 times 1. You can also write this as 4 times 3 factorial. Why? Because 3 factorial is just 3 times 2 times 1. Therefore, these two are the exact same thing, right? That's why we can rewrite this as n plus 1 times n factorial. Hopefully that made sense. Let me write it down. For n equals 3, if that helps you. So factorials are a little complicated, but whenever you try simplifying them, just to double check, always plug in a number, right? And see if you both get the same results. So I'm going to erase this. Now we're going to rewrite this, the n plus 1 factorial, as this. Why? Because as you can see, you can cancel this with the n factorial on the bottom. That's why we wrote it like this. So I'm going to erase this term really quick and rewrite it as n plus 1 times n factorial. So we know that we can, now let's just divide these two terms right here. Where's my arrow back? Okay, so we're going to have n plus 1 times n factorial over n factorial. These just cancel, so we're just left with n plus 1. So there's our first term that's simplified. Now let's simplify the powers of n. So we have 5n over 5n plus 1. Luckily this example is actually, it gave us a pretty good simplification. This was really easy to see what to simplify. So we're going to have 5 to the n over 5 to the n plus 1. This gives you 1/5. Now, there's 100 different ways to, maybe not 100, but there's a lot of ways to come up with how you know that 5 over 5 to n plus 1 will give you this. I also did the example last video, explained something similar, but I'll do it again really quick. So I'll do on the side right here. So let's think about it, right? First, this is one way of looking at it. You know 5 to the n plus 1 is just same thing as 5 times 5 to the n. So these two cancel, which leaves you with just 1 over 1/5. Right? Or if not, you can just plug in a number. Let's plug in a 2. So 5 squared over 5 over 2 plus 1, which is just equal to 5 squared over 5 cubed. If you remember, when you subtract exponents, when you're dividing by exponents, you subtract them, right? So what is 2 minus 3, -1, right? So this is also equal to the 5 to -1, or also 1/5. So 2 ways that you can see this, that y 5 to the n over 5 to the n plus 1 is 1/5. Now, conversely, if it was 5 to the n plus 1 over 5 to the n, that would just give you 5. And you can also prove it by doing the same things. But that's why. So hopefully that cleared some confusion. So now we can rewrite this, right? So we had the top, right? So this was just, so when we Well, my handwriting is terrible. I mean, my organization. Let's move this to the top. So this is just going to be equal to n plus 1 over 5. That's our ratio we get after simplifying this. So equals to n plus 1 over 5. Now we just take the limit, right? So the limit is n approaching infinity of n plus 1 over 5. So what is infinity plus 1? Infinity. What is infinity divided by 5? Infinity. Therefore the limit is infinity. And we know by the theorem for the ratio test that if L is greater than 1 or equal to infinity, the series diverges. So we can say the series when factorial over 5n diverges by the ratio test. And bang. Hopefully that wasn't too bad. The only complicated stuff of this series should only be simplification. Everything else should be straightforward though. So now we have example 9. Determine whether 2n plus 3 to the nth power over 5n plus 1 converges or diverges. So you see everything is raised to the nth power. It just screams a simple test. And what's that test? Survey says it's the root test, right? We're trying to get rid of the n. The root test gets rid of the nth power by taking the nth root. I think I said that right. Anyways, our term is going to be 2n plus 3 over 5n plus 1 all raised to the nth power. So we just gotta take the nth root of the absolute value of this term, and I'm stuttering. We don't really need to worry about the absolute value because this term is always positive, right? The 2n plus 3 over 5n plus 1, when you take the absolute value, you're going to get the same thing. So when we take the nth root, the root cancels out the exponent, so this is just, whoops, actually let me just write it. So this is going to be equal to nth root of 2n plus 3 over 5n plus 1 to the n. This, and this cancel out, which gives you 2n plus 3 over 5n plus 1. Now we just gotta take the limit, right? So the limit as n approaching infinity of 2n plus 3 over 5n plus 1. Now you can divide everything by n, but I don't know if you learned this, but whenever you take limits to infinity, whenever two terms have the same power, the answer is going to be the coefficients, right? So the highest power here is n here, and the top and bottom, right? They're both n to the first power. So I'm not going to erase that. So the limit is just going to be the coefficients in front of it. So this is just going to be equal to 2/5. And we know that for the conditions are that if L is less than 1 and 2/5 is equal to 0.4 and 0.4 is less than 1, and we know that this series, so we can say n plus 3 converges absolutely. By the root test. Now, if you don't believe that 2n plus 3, when you take the limit, is equal to 2/5, you can just divide everything by n, right? You're going to get, let's do it really quick, 2n divided by n is just 2, plus 3 over n over 5, plus 1 over n. Remember, 3 over n and 1 over n, as you plug in infinity, that just becomes 0, so it's just 2 plus 0 over 5 plus 0, which is also equal to 2/5. Sorry if I said that really fast, but yeah. So now we're going to move on to our last example, by far the hardest example. So we prepared. Determine whether negative 1 to the n times n factorial over n to the power of n is absolutely convergent, conditionally convergent, or divergent. I don't think you'll see this on a test. This might be a bonus problem, but actually I don't think it's too bad. You might see this on a test. So what do we see in this series? We see an alternating sign, we see a factorial, and we see a power. Now you're going to be like, you see an alternating, so that should scream alternating series test. That's true, but you also see factorials and powers. So you're like, you could be like, I don't know what test to use. I'm confused. You told me that if there's an alternative to scream alternating series test in my head. While that's true, there's also other things like factorials and everything, so it makes it different, right? So look at what to do. Let's look at what this question is asking. It's asking whether this is absolutely convergent, conditionally convergent, or divergent. That should be the key to what you do. So let's think about it, right? If a series is absolutely convergent, if we test absolute convergence first, we know that if the absolute value series converges, then we know that this series will converge. So that's the smartest choice, the first thing to do. So let's go ahead and take the absolute value of this big ass series. So we have from n equals 1 to infinity of the absolute value of negative 1 to the n times n factorial over n, oops, that doesn't look like an exclamation mark. We take the absolute value of all this, you know the negative 1 to the n just cancels out. So we're just left with series as n equals 1 to infinity of n factorial over n to the n. Now we do factorial, that should scream ratio test. So let's get our two terms. So we know our a sub n is going to be equal to n factorial over n to the n, and then we need a sub n plus 1, that's going to be equal to n plus 1 factorial over n plus 1 to the power of n plus 1. Interesting. So remember, I feel like the hardest part of this problem is just to know that to take the absolute convergence test first, because there's an alternator, a factorial, and an exponent raised to the nth power. So if there's like a lot of things that could be, and you're not sure, always do the absolute convergence test. Because if it absolutely converges, then the series converges. And normally when you take the absolute value, a lot of things simplify, right? So we got rid of the alternator. So we know that the series was n factorial over n to the n, and that made it easy to decide that we should use the ratio test. So now we got to take the ratio of both of these, remember? It's a sub n plus 1 over a sub n. So we'll do this on the side. So it's going to be n plus 1 factorial over n plus 1 times n plus 1 divided by n factorial over n to the nth power. Now we just take the reciprocal, multiply by the reciprocal. So this is equal to n plus 1 factorial over n plus 1 times n plus 1. Whoops, why am I writing fraction again? Times n to the nth over n factorial. All right. Well, let's get the party started, I guess. So I guess the first thing we can do is simplify these two, the factorials. Simplify this and this. So actually let's do it in blue. So we have n plus 1 factorial over n factorial. Now we know we can rewrite n plus 1 factorial as n plus 1 times n factorial over n factorial. And literally, I don't know if it was last example or two examples before, I proved why that was true. These two cancel out, which we get n plus 1. So let's rewrite this. Actually, I'm going to need space, so I'm going to delete, because I'm terrible at organizing my stuff. I'll get better one day, I promise. I'm going to erase all of this. So I'm going to go all the way back to the corner, in the middle. So actually, let's move all of this really quick. Oops. So we have one part simplified. So now let's just rewrite this, right? So this is going to be so you can write n plus 1 times n to the nth over n plus 1 to the n plus 1 power. Well, that does not look like an n. So if you know, we can separate the denominator, right? So it would look something like this. So this is also the same thing as n plus 1 to the nth power times n plus 1. So as you can see, the n plus 1's, well, let me do a different color, I'm sorry. In red, these two cancel out. Sorry, I need a water break. Therefore, this gives us n to the nth power over n plus 1 to the nth power. Since both of these are raised to the nth power, we can rewrite this as n over n plus 1, all of that to the nth power. Now we can finally take the limit. So the limit as n approaches infinity of n over n plus 1 to the nth power. So let's rewrite the inside. So let's just divide everything by n. So it's equal to the limit. So n approaches infinity. So remember, n divided by n is just 1 over, and n divided by n is 1 again, plus 1 over n. However, all of this is going to be raised to the nth power. Well, not the top right, because 1 to the n. So if I put an n right here, or erase this entire thing, whatever, no matter what n you plug in, this is always going to equal to 1. But at the bottom we have a plus 1 over n, so that's why we keep the n there, we don't remove it. So when you plug infinity, this is just equal to, well, the 1 divided by 1, this is just equal to 1. You can simplify this further to 1 plus 1 over n to the nth power, and that is just equal to 1 over e. This is a really famous, the limit as n approaches infinity of 1 plus 1 over n to the nth power is equal to e. It's a really famous, like, I forgot what it was called, but it's a really famous, like, limit. And I guess, I don't know why it's equal to e, but there's a way to prove it. I can make a video proving why it's 1 over e, but I just forgot right now, so I'll have to study up. But this is, like, probably not highly likely, like highly unlikely to show up ever on your exam, because there's no way your teacher expects you to know that the limit as 1 plus 1 over n is equal to e. Well, maybe if he gives you on a formula that, if he tells you, maybe then yeah. But basically the thing is, the only reason I chose example is because this one is really good, because you have to simplify a lot, right? Like, it looks really complicated when we first did the ratio, but you have to understand that you want to break it down piece by piece, and you want to try seeing what you can cancel. That's the main part of the simplification process. All the factorials, the powers, they do look messy and scary. Yes, I know, like, whenever I see them, I just want to, like, slam my head against the wall. I'm like, screw this problem, I want to skip it. But you want to understand that these are just really easy simplifications. You just want to find out stuff to cancel and ways to rewrite to cancel things out. So we know our value is 1 over e, and e, or Euler's number, is like, I forgot what it was, like 2.67, something like that. I was like, I forgot what it was, but we know 1 over e regardless. So I'm going to write this on the corner. So 1 over e is less than 1. Therefore, the absolute value series converges. So we can say because the absolute value series converges, the original series also convergent. So, sorry, the original series is also absolutely convergent. So, well, I guess in the small space right here. -1 to the n factorial of n to the nth is absolutely convergent. Sorry, I have no space, but that was probably like, I don't know, maybe the hardest example, but it's just mostly all these like root ratio tests are just simplification. I should just say ratio because root tests are really easy. So now let's go to our final recap for this section of series or the playlist. So remember, so just keep this in mind. When the limit does not equal 0, you should know divergence test. Constant ratio, that should scream geometric test. Exactly 1 over n to the p, that should scream p series. Positive, if you see a series is positive and it's comparable to a benchmark series or like a series you already know. For example, 1 over n squared plus 7, you know it's basically like 1 over n squared. As you plug in higher and higher values, think about comparison test. If you see alternating signs, that should scream alternating series test. If you see factorials or exponentials, mainly factorials, that should just go ratio test. Anytime you see a factorial, that's ratio test. If you see the whole term is raised to the nth power, that's the root test. If it's positive, continuous, and decreasing, and none of the other tests make sense, it's probably an integral test. So this should be your decision making and processing, and hopefully that helps clarify some things. If you want like another video of me doing more series for like different tests, if you want, like I can make like, I could do like, I don't know, for like if you comment like the most like or the test that you're struggling in, I'll make like a video of doing like easy and some really hard examples, and to show and to hopefully like help you understand the test and how to identify them better. But other than that, thank you. I hope you have a great day, and please like and subscribe, I guess, if you like the content.